I want to welcome you, for those who have not seen me yesterday, here at the University of Applied Sciences in Stralsund, especially in the Institute for Renewable Energy Systems. So I'm head of this institute and I'm teaching at the University Renewable Energies. One of my lectures is towards solar systems, another one is towards wind and hydro power. But we also have a lot of technology available here, especially in the lab, towards the storage of hydrogen. And that's what I want to show you today. And I invite you to have a virtual tour. We have to see how well that works, how well the camera holds up, and maybe at some stage, one of the many batteries that are involved might die. So be patient. I expect technical difficulties, so don't be mad at us, but hopefully everything holds up and we will do this adventure together. Maybe I want to start once more with a quick motivation towards the hydrogen. I showed that shortly yesterday, but I'm not sure and I don't remember all the names if everyone was there yesterday. But I want to start here on the board with a quick motivation towards the hydrogen. And we have the wind power plants, and we have our own wind power plant here just outside the lab over there, which runs partially the electricity here for our lab. And we also have a PV installation, right? So you have some renewable energy sources, and of course, there are other renewable energy sources. And we are here now at the Institute for Renewable Energy Systems. The renewable energy system is going to be huge. In the future, we will have not only wind and solar, but we will also have biomass. We will also have hydropower. We will also have geothermal power. And then there are other things like tidal power, so from the tidal waves, then wave power. So there's this entire mix of renewable energies, and they all have to work together as a system. And that's where it becomes complicated, and that's where we start with our research. But the most common renewable energy sources are wind and solar, because they do not depend on the location. You can build up wind and solar power plants basically everywhere in the world. Now, there are certain regions where you have less sun. Stralsund, for example, where we are right now, the weather is not really like summer, more like autumn, but still, solar installations work well here. Of course, wind power makes a lot of sense here in northern Germany. So these are, in the combination, a very good renewable energy source. How do we store that energy? Because wind is fluctuating. We could feel that right now very well if we are here. If I go outside, the wind is blowing in gusts, so you have a strong wind sometimes, then you have no wind for a short period of time. And of course, the sun is also fluctuating. That's no secret, right? At least in the night, there is no sun, everyone knows that, but we also have the fluctuation due to the clouds. Right now, here in our location, we have a cloud cover. Yesterday, we had a totally different weather situation where we had big clouds moving through and then blue sky and a lot of sunshine in between. So the renewable energies are strongly fluctuating in their energy production. So if we put that into a graph where we have here the electrical power as a function of the time, we can see that, for example, solar, and I'm just making something up here now, but it's kind of true, that solar, there it's easy, right? There's nothing in the night, and then over the day we have this hill, we have the peak of the production of the solar photovoltaic panels, and in the night there is no production. Then if we put maybe some wind on top of that, we can say, okay, here in the night there was a lot of wind, and then over the day it died, and then it was over the night, in the evening, no wind. So we have these fluctuating renewable energy sources. And then we have the energy demand. Okay, so let's make up some kind of energy demand here in red. And I hope you can kind of see hopefully you see the colors. Sorry for that, and thank you for your patience. And I hope everything's working again, and just interrupt us if again something like that happens. I was just about to draw here the demand, right? So let me bring you back to where we were. We have in yellow the electrical power generated by the solar fields. We have in blue the fluctuating wind. And then now in red, we want to add to that the demand, the electricity demand that the people have, that the grid has. So in the morning, everyone's sleeping, then people get up, they maybe make some coffee or so, and then they drive to work, and at work, the machines start and they start up their computers. So over the day, there's a pretty high energy demand. And then in the evening, everyone goes back home, and maybe people watch TV, and then everyone goes to sleep, and the next day can start. So we could say this is one typical day on the energy side. And for those of you who have some knowledge towards the electrical part of a grid, they know we always have to have this balance between production of electricity and consumption of electricity, okay? They must be at the same level. We cannot have too much production as we would have here, and we cannot have, as we would have here, too much consumption. So we need to store the energy. Here in there are certain parts where we have too much electricity and other parts where we don't have enough electricity. So we somehow need to store that electricity. And how that works with hydrogen is something that I want to show you now on a little experiment that we have installed here. And let me see, low video resolution. I don't know about the video resolution. If it's really bad for everyone, please tell us, or maybe reload the conference, but normally it should hopefully be fine. We have here a little experimental setup that shows exactly what I was doing over there. We have a sun, and that is this lamp here, which I can switch on and off. So we can simulate sunshine and night. So let's switch our lamp on. Then we have a small solar panel here. And from this solar panel, let's see, there are a lot of cables here. From this solar panel, I can measure the voltage, for example. That's rather boring of a solar panel. And you will have a lecture on solar power later today in the afternoon. So ask colleague Kur about some of the details here. So you can see this solar panel creates about 2.2 volts of voltage. And if I want to measure the short circuit current, I can directly go to this one as well and can see, okay, now it's generating 0.3 amps. What happens now if I move my lamp around, and if you can see probably, yes, now there are some clouds, now the sun is shining again, and all I'm doing is I'm moving the lamp, and you see the renewable energy production is fluctuating, okay, and we cannot control it. So we need to somehow store that energy. We can also consume that energy. We can say, here, let's use this electricity and let's drive this little motor here. So this is probably bad in the video because it's moving really quick. This little ventilator, this thing starts to move. You see, it starts rotating, and the frame rate will for sure not pick that up. But if I just start and stop it, you will see it starts rotating. And I mean, there's no real magic behind that you can run an electric motor with the solar power. There's no big secret to that. Now I want to use this electricity in an electrolyzer, and I want to produce with this the hydrogen. So let's connect that here to our small electrolyzer that's up here. And if we do it like that, we should see, so maybe I'll move this over here. So now we have the electricity that we just showed is working, that it's coming out of this solar panel. This electricity is now going to the electrolyzer. And an electrolyzer splits the water molecule H2O into hydrogen and oxygen. So let's see if something is happening or not. Maybe we have to take the lamp a little bit closer, and maybe we have to wait for a few moments. But normally, if we have done everything correct, it should start to form little bubbles. And these bubbles are then, of course, in the liquid, rise to the top. So we should see, and if we come really close with the camera, we see that right there is some bubbles forming now, and they leave the membrane, and then they rise up. So you see there is a production of gases starting now. It is not much. Our solar panel is slightly too small for this electrolyzer, but you see the process of creating two gases from a liquid is actually happening. Again, no big secret. Something you have all probably done in your chemistry lessons in school at some stage, right? You now can see there's 2 times more hydrogen than oxygen and these kind of things. So let's leave this here for a moment, and we will collect some hydrogen. Let's see how long that will take. I will take care of a few things first for the next part of the experiment later. Okay, so now we let that bubble. We let that bubble around for a while. We will collect some hydrogen. We will have a surplus of energy for a while because there's no energy demand, right? Our little wheel is not running our electrical motor, so we are only producing electricity too much and we cannot use it. So we store the electricity by going towards the hydrogen production. This does not only work in such a small scale, but in a slightly bigger scale. And we have another electrolyzer where this is nicely shown. So come with me through the lab, and on the way there also you get a feeling, maybe at least, for what else we have here on the other things in the lab. And I'm just looking at the chat if there are questions or not. So we have another electrolyzer just here. It's a totally different technology. The one we were using over there is an electrolyzer that is using what's called PEM technology, proton exchange membrane. This one's an electrolyzer, an alkaline electrolyzer. And you see there are many more details, and we could just have an entire lecture about the differences between PEM electrolyzers and alkaline electrolyzers, but maybe not today. What I want to show you now here is that we can not only have one of these membranes, but we can have several of the cells in series for a bigger production of hydrogen. So if I go to the other side, we zoom in and we can see that you have several of these cells all in series. And right now, nothing is happening because over here, our current is still 0. So we will look at the electrolyzer inside. You see the potassium hydroxide inside. That is 30% potassium hydroxide. And now that we plugged it in, you see the first bubble starting. So maybe if we look at it, we can see really close that there are little bubbles starting here on the cells. And if I increase the current, there should be quite a few bubbles coming up. And at least here in this top row, then you can see something is happening there. We are now producing hydrogen. And not only a few small bubbles, as you just saw on the other one, but now we're really producing hydrogen, okay? And we can see over there that there is hydrogen bubbling out, and that is where we are collecting it. And on this little example, we can see all the parts that we have in a real electrolyzer. In a bigger one, we need these cells. This is the actual electrolyzer. And then we need the so-called gas separator, because the alkaline solution down here, our potassium hydroxide, it creates hydrogen foam. So it does not directly let the hydrogen bubble out, but it has hydrogen foam. And that is difficult to see, but over here you can see there's these bubbles, there's this foam, and that needs to be separated. That's why we have up here on the top part, we have our, here on the top part, we have our gas separators, where we have these little just plastic pieces inside that help to pop the bubbles of the hydrogen foam. And then the potassium hydroxide flows back into the electrolyzer, and the hydrogen is then washed. And let me actually set the current to 0. Let's turn it back on. And now you see again, it's again bubbling. And over there, we have what we're calling the gas cleaning, or then the gas preparation. So we have gas separation and then the cleaning over there. And there we let our hydrogen just bubble through water. And what we can do now over here, we can collect that hydrogen. So if we have a little experiment, let's try that together. Here I put this little tube on top of that hydrogen outlet, and now I can collect the hydrogen bubbles. Yes, and you see that there will be hydrogen collecting up there. And you see that slowly the hydrogen is pushing the water out, and now we are collecting hydrogen. And with our students, we do this as an experiment together. We measure the time it takes to create a certain amount of hydrogen, and then we increase the current. We play with the voltage, and we see the voltage doesn't do a difference, but the amount of hydrogen that we create is directly proportional to the current. That's Faraday's law. And we always try to teach everything on a very practical level. Okay, and so this is the special case here in our lab, that we have all of this equipment available. And if you're here and if you're studying here together, then we have the option to do these kind of experiments together. And we are learning not only on the blackboard, but we are learning together in experiments. And I think that helps a lot for the understanding, because you can really see yourself, not only that hydrogen is bubbling out, but also that the hydrogen is not directly exploding. We want to ignite some hydrogen later as well, to show that, of course, you can switch the hydrogen to the explosion mode. But for us here, we always need to take care with hydrogen. Safety plays a role, of course, yes, but we are in a big hall, so this bit of hydrogen that's bubbling out here is not a problem. So if we talk about safety right now, then maybe we should talk about hydrogen and its explosion levels. The lower ratio is at 4%. So if you have 4% of hydrogen in the volume, then you have an explosive mixture. That's why we have hydrogen sensors under the ceiling at different locations, where there is a measurement point, and these give a warning signal way before the 4%. So we will never have this explosive mixture. And then the other part of not having something explode is, do not ignite it, right? I mean, here hydrogen was just bubbling out, but if I do not put fire to it, like a lighter or some extra heat source, then the hydrogen does not ignite. So if you know what you're doing, hydrogen is quite safe to be as a storage method. Hydrogen can be used in many ways. And let's see if the connection stays up. If we go through here and look at our motor, I kind of have to squint through here to see if the connection's there. Yes, so I can see the picture. That looks good. And here we have our motor, a CHP. This is a combined heat and power plant. It is an engine that is capable of running on hydrogen. So it's just a normal combustion engine, normal internal combustion engine, but it's capable of running on hydrogen. So we can use our renewable energies that are fluctuating, that are going up and down, to produce hydrogen, but that's only the first step. Of course, in the end, we need electricity again many times, or we need, like here, this motor could also be used for mobility. So we need other solutions. We need this hydrogen to store the energy for us, and then we want to do something with it. And in this motor, we're not only testing to run it on hydrogen, but we're also testing to run it on methane, on natural gas, and the mixture of natural gas and hydrogen. And these are research projects that we are doing here in our lab. And so we do with our students together this work where we have the students learn basics, like we just did on the electrolyzer with some of the basic things. And then we do also research work together with the industry in projects together where we start to have the industry interest. And they ask us, okay, what are we doing now with our natural gas grid? Yeah, so we have the natural gas grid, and with this natural gas grid, we want to know what will be in the future in these gas grids. Will we have only natural gas there? Probably not, since we are doing this whole turn towards the renewable energies, and we are now turning towards using other technologies, and we want to use hydrogen now as a storage method. So we want to go through a transition where we have renewable energies stored into the gas grid. And we can use this good gas grid that we have in Europe to transport renewable energies. We have in northern Germany here enough wind to supply a lot of the energy. But how do we transport that to where the industry is? And one solution is the gas grid. But how do we put hydrogen into the gas grid? Can we just mix that? And that is one of the questions that the industry has. How are we doing that transition? Are we putting directly a new hydrogen grid there? Well, no one wants to pay for a second infrastructure. Are we switching off the old grid and switch it directly to hydrogen? No, that doesn't work because all the end consumers do not change their consumption to hydrogen right away. So we will have this transition where we mix hydrogen to the natural gas, and then from the normal natural gas connection in the houses, we do not get pure methane, but we get also a mixture of hydrogen. And that has to be green hydrogen. And then partially we get into this discussion of having an emission-free heating system at home where we have less CO2 emissions, because that's where we need to go, right, due to the climate change, less CO2 emissions also for heating at home. So the hydrogen that we are using, and brings us back to the board here, where we say, okay, we now use the electricity here to split the water molecule into hydrogen and oxygen. So we use the electricity from the renewable energies to split the water molecules into twice as much hydrogen as oxygen. And this hydrogen now is our energy storage solution. We have looked at an electrolyzer that over there is still bubbling and collecting more hydrogen. That's good. We looked at a bigger electrolyzer over there that is very close to another even bigger electrolyzer that we have here at the university. We have a 20 kilowatts electrolyzer here that is working exactly with the same technology as we saw in this little experiment over there, just a lot bigger and of course not made in a see-through mode. It's a special one where we can see the bubbles over there. The other one is all made in steel and you don't see anything, so it's actually pretty boring to show on a camera. I think this one's quite nice because there we can see something moving. So we get through the electrolyzer the hydrogen. You might ask, what is the efficiency? And someone asked that already yesterday, the efficiency of such electrolyzers. And the efficiency is in the range of 70 to 75%. So we can write here an efficiency of 75%. That is a number that is easy to remember and that is easy to calculate with. The system efficiency normally is slightly lower. The cell efficiency sometimes is even slightly higher. It really depends on the details then, but I like these simple numbers with which I can calculate in my head quickly, and then I just know, okay, maybe this is always lower or this is always higher. So let's stay with this simple number of 3/4 of the energy that I get from the renewable energies is stored in the hydrogen. Now, this hydrogen I can use for many different applications. One of the applications we looked at yesterday, and that was the mobility. So we have here maybe a little car. So that is driving on hydrogen. We don't need to draw any exhaust fumes because it is driving emission-free, and it's driving very clean, and it's driving very efficient. And how that works in the mobility, I want to show you now with our little hydrogen race car that we have over here. So we have a little hydrogen race car that we built with our students. We have the, oh, there you go. Okay, it's on this little stand. And so one person has to fit in here. Yes, this is where a, small and lightweight person has to sit. It's okay, people fit in here, don't worry. That is okay. But the interesting part, the technology part, that is over here. And if you come a bit closer, we can see inside, and we can see here our hydrogen bottle. This is where the hydrogen is inside. And after the 200 bar storage of the hydrogen in the bottle, we go through a pressure reducer unit to the actual hydrogen counter, and that is here. This is the basically most important part, so to say, because we are taking part in a hydrogen race, in a competition. And in this competition, it's all about the consumption of the hydrogen. So we are looking for the car that has the least consumption of hydrogen, the most efficient car. So there's not only this car in the world, there are many of these, and they are all built by students. And then there's a big competition where every year all of these cars, all of these teams meet, and they drive on a track against each other. So they drive at the same time, not all of the same time, but many of them on the same road at the same time. And you have to drive a certain distance in a certain time. If you are too slow, you're out of the competition. If you are too fast, you have consumed too much energy. So it really is an interesting part of that competition always to be just in time on the goal line. So you have to drive as slow as possible, but as fast as needed. And the mean speed of that car for that competition is 25 kilometers an hour. So it's not really a race car, but still in this little car without any dampeners or anything like that, 25 kilometers an hour feels amazing fast. Anyway, so we drive on that one, and then after about 45 minutes of the race, then the officials look into this little piece. That's why I said it's the most important one. And then they can read, now it's switched off and you can't read anything, but then they read off there how much of the hydrogen we consumed. So it is directly after the bottle, after the pressure reducer, this little device is counting how much hydrogen we are consuming in these 45 minutes. And then the way more interesting part starts. So if you keep following this tube here, we get into our fuel cell. So we built our own fuel cell here, and it looks not only complicated, but actually is complicated because we really had so high demands on our fuel cell that no company could really build that. So no money can buy that fuel cell that we have here because it is really a development only for this race car. And the success of the last years tells us that we are doing something right, because the car, or at least the technology you see here, is the world's most efficient hydrogen prototype race car. We are driving since 2008, not with this car, but in a development series. Okay, so you will see tomorrow no, on Friday, not tomorrow, but if you get into the right session on Friday, there is a session from this Tiger team, and then they can tell you more details on how that works. They will show you the workshop, and then there you can see really how this thing is built. They will tell you more numbers maybe about the race car and about the race itself. So I don't want to give away all the secrets now already, and then you don't join on Friday. So please come back there. This is a really cool project, and I like it because our students get the opportunity to learn all of these things really by themselves, and they can work with that. So they don't, sorry, they don't only learn things on the board, but they also learn things by actually doing things, not only in experiments, but really experiment themselves, building a race car, sitting in the car, being part of this race in the end. So let's see maybe what our experiment over here is doing if we have already collected some hydrogen. And yes, you see about 20 milliliters of hydrogen have been collected. Now the water line is lower here. So up there we have now some hydrogen, and right there is the water line. You see that, and we have many of these little bubbles collected already. And you see, this technology enables us to collect small amounts of energy, and each individual bubble by itself contains energy, and in the end we store some of the energy. Now we want to use that energy, and I told you there is technology like a motor, like an engine. There's technology like we just saw here in our race car with the fuel cell, and we have a fuel cell here as well. Let's see if we can get the cables from the fuel cell. So here's one, there's one. They go to all kinds of different places, and let's connect them to the voltage measurement that we have here, to the voltmeter, and see what the fuel cell does. Well, oh, it already has a voltage. That's good. So there is hydrogen at the fuel cell. And you can see the fuel cells. It's actually two of them together now, two of them connected electrically in series, one cell and another cell up there. And together they are producing 0.8 volts right now, as this little voltmeter shows here. Let's see what happens if I purge on the hydrogen side a bit. If we get slightly more, so I'm opening a little valve here, a tube, I'm letting some of the hydrogen through, and if I take my hands away and you see the numbers again, you see it jumped up. So now I pushed hydrogen through this tube, through the fuel cells, and I brought more hydrogen to the fuel cell. We can do the same trick here on the oxygen side. That should have almost no effect, but maybe a little one. Let's see, or nothing happens. That's also interesting. See, that's the fun part about experiments. That nothing works, but no, there you go. Okay, so making sure that all the tubes are not stuck or anything, so that did almost nothing as promised. Now we can use that electricity from the fuel cell to run our motor again. Here, connect this one there, and then there's another cable here. Let's see if the motor is running. Yes. Okay, so again, I'm doing this in a kind of like a start-stop mode so that you see how it starts and runs. And if I connect that, you see it's now running. It's consuming some electricity. That's why the voltage drops, because now you have current flowing through there, and all the technical parts. But the most simple part now is, if I switch the light off, if I take the sun away or just unplug the sun, then it's still running, right? It still is running here, and we are now independent of our fluctuating energy, renewable energy. We can now use it when the sun is shining to produce hydrogen, and if the sun is not shining, we consume the hydrogen. Okay, so we now have this full combination of using electricity to produce hydrogen and using the hydrogen to produce electricity again. So let's maybe get back to the board and let me explain to you how that hydrogen fuel cell works. We have a membrane, and we will come back to that in a moment. Yes, thank you for the remark there in chat. So we will come back there in a moment to have a closer look. We have a membrane in there. Maybe some of you already saw that. That is this membrane, that is this fuel cell that is standing right there. And from one side, we are getting the hydrogen, and from the other side, we are getting the oxygen to that fuel cell. And now we need to know that this membrane is called a proton exchange membrane, PEM. And I already mentioned PEM earlier when I was talking about this electrolyzer over there, because the electrolyzer works exactly as I'm describing the fuel cell now, just in the inverse direction. So it is called a proton exchange membrane. It's a plastic material, so to say, it's Nafion, and it is capable of conducting protons, and only protons. So electrons are not conducted, and something is telling me that I'm having no connection, but the other one shows that we are connected. Okay, just watching the technology from time to time. I'm hiding behind the host logo here, but that's fine. Okay, so we have the hydrogen coming in from one side, and hydrogen, being the first element in the periodic table, consists of protons and electrons, right? The electrons move kind of in a circle around the proton, and then we have this hydrogen atom. So we have now a membrane here that lets the protons through. So let's here draw some protons that can go through the membrane. So what does that do to the electrons? The electrons are left behind. We get a few of these electrons, and they are very sad because everyone is over there on the other side of the membrane. Okay, their entire family, everyone get over there, and they are left behind. That's not nice of us, so we should collect them. Okay, so we give them an electrical connection, we give them a wire, and we let them go over there as well, so they happily follow along here and get to this side as well. Then the protons, the electrons, and the oxygen are being combined again to produce water again. So this reaction that we still see over here, this reaction is now being done backwards, and that reaction is hydrogen plus oxygen creates water. By using a proton exchange membrane that lets only the protons through, we trap the electrons, and we give the electrons the option to flow through this wire. And if electrons flow through a wire, we're calling that a current, an electrical current. So we can use these electrons to drive either here a lamp, yes, or as we saw in the little experiment, an electrical motor. So we can use these electrons to move over there. If we want to be really mean to them and don't let them reunite with the rest of their friends, we could just put here a switch and measure the voltage. So to say, we want to measure the force, the power with which these electrons want to get there. Okay, technically speaking, we are talking about the electrochemical potential between hydrogen and oxygen. So the electrons want to get to the other side with a force of 1.23 volts. So one of these fuel cell cells, a single membrane, can produce 1.2 volts. In theory, practically, it's less. It's closer to 1 volt. Who remembers the voltage that we had over there in the experiment? Let's see who's awake. Let's do this a bit interactive, and let's see. I can read the chat from here. Which voltage did we just have over there on that experiment from the fuel cells? Who remembers? Yes, some people are awake. That's great. Thank you. Exactly, 1.6 volts, about 1.67, 1.6. So that means if we have two of them electrically in series, we got 0.8 volts out of them. That is pretty good. That's pretty normal. 0.8 volts is for a fuel cell quite okay, especially if we keep in mind that they have been in this configuration for a very long time already. Yeah, let me hold that for a moment. You plug something in, and I'm going with you again to the experiment to see what is going on over there. Now I'm behind the camera and I can keep talking. We can do that still together. You see these 0.6 volts, they tell us that the membranes that we see up here, let's see if we can see that. There is the membrane of the fuel cell. If I go around it like that, then you can see that these are these membranes. And you have from one side the oxygen connection, and then from the other side there we have the hydrogen connection. And then we have two of them put together in series, and they produce these 0.6 volts. And that's why to produce the voltage that we need to drive a real engine, to drive like our race car, or to drive later on bigger applications, we need several of these cells in series. So if we look at a fuel cell, and we have one over here, we will see that always in a fuel cell there are a lot of individual cells put into series, all behind each other. And this is a fuel cell module, and we can look inside here from the top. Let's see if the camera picks that up, where we can find out that we have a lot of individual cells now here in series. You see, there are several of them all lined up like that. So we can, so there's we open that up so we can look inside, and there's a little piece of glass in front of it so we can look inside. And you see there's one cell, and then another cell, and another cell, so several of them behind each other. It is a fuel cell module that is being sold by a company. So it's not something that is in the development stage, or something where in the lab people try to find out how that works or so. But it is something that you can actually buy, and it has like a brand name, and it has here just an on switch. Okay, so nothing but an on switch, so it's easy to use by a customer. So fuel cells are definitely in the range where we can use them and bring them out into the market. The fuel cells are quite efficient, so we need to talk about the efficiency again. We said here we have an efficiency of the electrolyzer of 75%. The fuel cell efficiency, being very technical here, but okay, that's okay. If we take the fuel cell efficiency as a function of the power, so to say, it is going in a way like that, so that we have a high efficiency at the beginning of the power curve and a lower efficiency at the end of the power curve. And in the beginning here, we can reach 50, 60%. So let's be optimistic here with the 60%. And so then here at the end of the working curve, we are at 30% efficiency. So the efficiency of such a fuel cell, the efficiency of the back transformation of hydrogen back to the water is around 30%. If we are optimistic, we can say, okay, maybe 50%, but somewhere in the range between 30 and 50% in the back conversion. And that's where this whole discussion starts about the bad efficiency of the hydrogen technology. And I told you yesterday about battery electric cars and fuel cell electric cars, that of course with a fuel cell electric car you have certain advantages, but one of the biggest disadvantages, you need a lot more of the renewable energy sources. Yes, you need many more wind power plants and solar power plants to produce the same amount of kilometers to be driven by a car that's running on hydrogen. But we can store the energy, and that's where the advantage comes in. We don't want to charge our battery electric car only if the wind is running, right? We want to charge it whenever we want to drive. And so we can use this stored hydrogen that we already needed to keep our energy system stable. This stored hydrogen we can now use to drive our cars. So we drive our cars by hydrogen, but also we can use this to produce electricity again in a bigger scale. So for times when there's no wind, when there's no sun, in winter there's a lot less sun, especially here in Northern Europe. There's a bit more wind sometimes, but even though in January, February, we sometimes have these 1 or 2 weeks of almost no wind and very little sun. So we need to store energy. We need to bring back electricity through this storage loop of hydrogen. And then we also have the demand for heat. Yes, I mean, winter is coming and heat is in red normally, right? So let's draw something like heat flames here. So we also have the demand for heat. And also something that can be done by hydrogen. Quite simple. I mean, the simplest one is to just burn the hydrogen in an open flame that gets ridiculously hot. Or you can use a combined heat and power plant, as I showed you over there. You get the heat from that one as well. So combining electricity production and heat production. And then there's one more very important path to use the hydrogen. And let's again do something interactive here and ask you, I want to ask you, does anyone know where we use hydrogen already today? I mean, not in either of these, right? But in the chemical industry, where do we use hydrogen? Does anyone know chemical reactions that use hydrogen and that we need in the end some of these molecules? So what are we using hydrogen today for? And I'll clean a bit of the board so that we get some space for further comments here. Who has an idea what we use hydrogen for? Well, there's only very little feedback on that, so either everyone's asleep, away from the computer, or people don't know, which is also fine because it is not commonly known that we need a lot of hydrogen. And we need hydrogen in the mineral oil industry, so every time we use gasoline in our cars, there has been a lot of hydrogen already involved. Hydrogen is a very important part of fertilizers. So in ammonia, NH3, there's hydrogen. And a lot of hydrogen in the ammonia, which is one of the main parts of fertilizer. And where does this hydrogen come from? Well, quite simple. Right now, it comes from CH4. We are using natural gas. We're using the sources, the fossil sources that we have to get hydrogen. So this gives us hydrogen, and hydrogen plus Nitrogen gives us ammonia. So now we need to be careful with like N2, and so we need 2 of these, and that gives us 3 of these. So with 3 hydrogen molecules, we can produce 2 ammonia molecules. And that is something that is done right now in the entire world on huge scales. But if we look at the other parts of this reaction here, how do we get out of CH4, out of methane, hydrogen? Well, what else do we release? If we look at that, well, what do we do with the carbon? We get CO2, right? So what we do is we have CH4 plus H2O. So we take methane and water, we combine them, we take the oxygen to get, and then we have here a 2 and so on, more details involved. But the carbon and the oxygen from the water react to carbon dioxide. The hydrogen is released, the hydrogen is used in the industry on a big scale, and we're releasing CO2. And I think we all kind of agree right now that releasing CO2 is not sustainable. We are doing something to the world's climate, to our atmosphere, that is not good. And to keep doing that is not a good idea. But to not produce ammonia is also not an option. We need ammonia to feed the world, because ammonia is, as I said, the main part of fertilizer. You can also use that for weapons and explosives, but okay, that is not really where I want to go. So this is fertilizer stuff, and we need that to feed the world. So we need the hydrogen. But we still have on the same board a very nice solution for green hydrogen. So let's use this green hydrogen for that reaction. Let's get rid of that. Let's get rid of using CO2 or emitting CO2 by using fossil fuels. Let's use green hydrogen. Now you might ask, that sounds simple. Look at him. He's just doing one arrow and then he's saving the world. Well, we have to keep in mind the price of the hydrogen that we are producing. Let's talk about this hydrogen over here. This is what's called gray hydrogen. This hydrogen has a price of roughly 2 euros per kilogram. 2 euros per kilogram is roughly the price of that hydrogen. That is already containing the price for the methane that you're buying. That's already containing the the plant that's producing the hydrogen. That's already containing the CO2 taxes that are being paid right now. If we are producing hydrogen from a green source, there is right now almost no way to produce green hydrogen for a cost of less than 4 euros per kilogram. So twice the price. And if we are honest and if we take everything into account, it's probably more. So at least a factor of 2 in the price. If we want to just paint this guy green, do we have green chalk here? Yes. So let's draw that green to make that green hydrogen. Then we would have a sustainable way to produce ammonia for fertilizers, but for twice the cost of the hydrogen. Nitrogen doesn't cost anything, so basically that makes the nitrogen, that makes the ammonia twice as expensive. And we all know that people are not going to buy expensive food, they want to buy the cheap food, and at some stage we need to feed the entire world. So I want to show you a few more things over there towards hydrogen storage solutions, and we will come back to the ammonia through that discussion over here. It's good. Okay. So here we have a few things that explain us how hydrogen can be stored. The most simple way to store hydrogen is by just putting it under pressure. So I've got a few balloons here, and if you would be here, you could try yourself. So this is just a piece of a balloon, right? And maybe you have a balloon in your room or somewhere close by. and you fill it halfway or you fill it all the way, it doesn't really matter. But try to reduce the volume of this balloon by 2. Okay, just make it half the size. Okay, just try that with a balloon at some stage, except for it making funny bubbles. You will probably not have enough power in your hands and arms to reduce the factor to the volume. And that would correspond to 2 bar. What we do with hydrogen is we compress it even more and even more, all the way to 700 bars. That would mean that you take your balloon and reduce its volume to 1/700th of its volume. That gives you an imagination for the amount of force, the amount of power that is used to compress the hydrogen, and also the amount of pressure it has then. That's why you need these strong vessels. And let me come closer to the camera so it picks it up, how it is built up. So you have a metal inside, and then on the outside you have these carbon fiber layers, and they keep the pressure inside. And by lifting it, you can feel it has a certain weight. This is a part of a pressure vessel that is normally in hydrogen cars. Yesterday in the lecture, I showed you these hydrogen cars driving on 700 bars, and I showed you how these tanks are in the back of the car over the length of the car. And this is heavy, okay? I'm just a strong person, that's why I can lift it easily, but this is heavy. So we have yesterday in the slides these numbers: 6 kilograms of hydrogen and many, many more kilograms of the infrastructure around it. And that is such a high pressure vessel here for the hydrogen. So you not only do you lose energy by compressing the hydrogen so much, but also you lose efficiency by having this high rate and so on. So we are looking into other ways how to store the hydrogen. You could go to liquid hydrogen. Liquid hydrogen is stored at very low temperatures. Hydrogen only becomes liquid way below 250 degrees. So it's really cold. And that is not good, because it takes heat from the outside, it starts to boil, and it loses hydrogen, or it builds up a pressure and so on. So liquid hydrogen, well, that's something, if you want to use a lot of energy in a very short time, like going to the moon, and the Saturn V rocket was driving on liquid hydrogen. So there are applications for liquid hydrogen, not really in our everyday world though. There have been experiments also with cars. BMW has been experimenting for a long time with liquid hydrogen for their cars. Then they got rid of that idea. Now basically everyone is using this pressurized hydrogen. You can also store the hydrogen in metal. It's called a metal hydride then. And these are complicated chemical compounds. So it's basically pure metal. This whole thing is just pure metal, and the hydrogen is filled in, and then it is stored in here inside the metal structure. So the hydrogen really is bound into the metal. It's called a metal hydride then, and it can store a lot of hydrogen in this very small bottle. So in here we have 200 liters of hydrogen. So if you take my average human size, you can see how big that is. And if you imagine, in here are 200 liters, that is from the normal standard German milk canisters, 200 of them all stored in here. However, the pressure of this one inside is really low, because the hydrogen is not compressed physically, but it's kind of chemically bound inside the metal. But that means, again, it's not so easy to get it out. So you have to heat them up to get the hydrogen out. We have another version here. This one's so heavy, it's even on wheels. Let me move that forward. So there you go. That is our other bigger metal hydride storage. And if you look from the side, you can see there is like a water inlet, so you can put that into warm water here, and then the hydrogen comes out. And that is a very nice and safe way to store hydrogen. However, and kind of demonstrates that by the wheels, right? Very heavy way to store hydrogen. Heavy is not good for mobility, not good for cars, but it does work in submarines. So it's not a big military secret, but in German submarines, we have such hydrogen metal hydride storages and fuel cells so they can be really quiet and efficient underwater. So there's a lot of research going on towards metal hydrides, and again, always a lot of people invent new materials, lighter materials, materials that release the hydrogen at lower temperatures, and all kinds of things. But now it's not really an economic solution to store big quantities of hydrogen, at least not for mobility and not for transportation. For stationary ones, maybe, but then the cost again is pretty high. So we have to find other solutions. And other solutions are then going towards liquids again. One example we already had on the board, that was ammonia. We can use ammonia. Why not use NH3 as a storage for hydrogen? We can produce the hydrogen all over the world, maybe Northern Africa, maybe in Iceland where there's a lot of geothermal power, and then take that hydrogen, produce ammonia, and have big ammonia ships drive over the ocean. I don't have ammonia here, I have methanol here. It's another solution that contains as a molecule a lot of hydrogen. Methanol has the big advantage that it's not as toxic as ammonia, okay? Methanol is also toxic, please don't drink methanol. But it is at least a lot easier to handle. I can open it without us all running away due to the bad smell of ammonia. It has another big disadvantage. It does not need nitrogen, but CO2. Okay, we can write the formula on the board if there are questions and interest in that, but what the reaction is, it's now using CO2 to produce methanol. And that's exactly one of the laboratory installations that we have here is a little methanol plant to produce from our green hydrogen, green methanol. So we use CO2, but where do we get it from? We can get CO2, in our case, from biomass. We get this from biogas plants. You can get that from burning biomass and other means as well. But in the air, there is only very little CO2. So direct air capture is a huge research field to get the CO2 out of the air, not only to reduce the amount of carbon dioxide in our atmosphere, but also because we want to use carbon dioxide now to store hydrogen, either in methanol or in methane, or even going to what's called e-kerosene and e-fuels. So having even bigger and longer carbon hydride chains. Hydrogen is a very difficult substance to store. It works quite nice in methanol. It works quite well in ammonia, but also works with dibenzyltoluol, an even more complicated molecule now that is in a liquid form here, such an oily substance. This is already used all over the world as a heat transfer fluid. So it's just an oil that has this light yellowish color that doesn't make it look too nice. But if you let hydrogen bubble through this at the right temperatures and with the right catalyst, it becomes transparent. This liquid now is basically chemically almost the same, but it contains a lot of hydrogen. This hydrogen is chemically bound, very similar to our ammonia that we just had on the board. So simply speaking, carbon double connections break up and store the hydrogen in there, so we get this one. And so I can open this one up. There's no hydrogen coming out. It does not ignite directly the hydrogen or anything. It's a very safe way to store the hydrogen. It's called LOHC, liquid organic hydrogen carrier. Yes, that is the big advantage of these technologies together with this methanol as well, because you can now quickly fill your car up, fill your tanker or whatever is transporting your energy. Because you have a liquid, you can just pour it into the next vessel. This really has the advantage of having enough hydrogen, similar from the volume as if we would have compressed our balloon to a 2,000th of its size. So speaking about the volume, it contains as much hydrogen as a pressure vessel at 2,000 bars. Speaking about the weight, this is of course way more heavy by the liquid itself, but the system is way lighter because we don't have a pressure vessel at 2,000 bars. We just need a normal, here it's a glass bottle, but we can use normal infrastructure as we are using it now with diesel or gasoline. The same infrastructure can use these LOHCs. It can also use the same methanol. This has a higher energy density again than this one. This is a more complicated technology. So this is done by a company here in Germany, the Hydrogenius company. They are kind of like invented that, and they are now selling these liquids and the technology with it. With the methanol, there's also a lot of industrial research and a lot of industrial interest going on. And on the other side, towards ammonia, we are now in a big research cooperation where we are trying to find out if we can use ammonia as a big energy storage solution. That there is energy in the hydrogen, I want to show you with a little experiment now towards the, well, not really the end, but maybe as an intermediate end or so before we can go towards more questions and a longer discussion on other sides. So let's see, I have here hydrogen from our metal hydride bottle, and if I let some of this hydrogen slowly bubble out through the tube, it is going into a soap solution. And in the soap solution, the hydrogen makes bubbles, it makes foam, and this foam now consists of hydrogen bubbles. And hydrogen is lighter than air, so hydrogen goes up, and therefore the foam will rise. And we see here now it's going up, and we can see that the hydrogen foam is rising. You can maybe even hear the bubbles bubbling, but that's not too exciting. And so now we can see this is something you cannot easily try at home because normally you don't have hydrogen there. And so it keeps rising, it's lighter than air, and it makes these nice, looks almost like a cactus or something like that, hydrogen foam structures. So let's see if there's energy in it. Let's ignite it. Let's make some experiments with fire. So we have here a little tool with which we can ignite things from a distance. You can see it is also good to motivate students. And if we put that close to the hydrogen, you get the nice flames out of the hydrogen. You get this little, well, explosion, it's not really, but combustion where we have the hydrogen used in an energy form, not very efficient, but if we have fun, it's also some kind of efficiency. Let's use this point that everyone woke up from that boom to answer questions. Let's see if there are any questions over here, and please feel free to ask questions, to go through things that are interesting to see, and we want to see if there are questions that you have, things that you have maybe heard somewhere else that you always wanted to ask in this direction. And if there are no direct questions, we will just do the experiment with the hydrogen again and again and again till everyone is happy. We could also blow up a hydrogen balloon and try to, fill a balloon with hydrogen and try to ignite. This one also makes boom. It's less impressive through the camera. This one I think is nicely to be picked up with the camera. We also have a little experiment where we directly have brown gas, so hydrogen and oxygen gas mixture very explosive, and that balloon really gives a big a boom there. So of course, hydrogen is dangerous. Okay, I mean, you just saw this little amount of hydrogen being already in a quick combustion, and hydrogen is one of the most flammable gases there are. And I already said earlier, right? You need to be careful if you handle hydrogen. We are handling hydrogen here in our laboratory for more than 25 years, and we never had an accident. But we know what we're doing. Right, we take care of the things. We make sure that there is, for example, no hydrogen collecting under the roof, or at least that we have sensors there. Hydrogen goes up, and so if we have a hydrogen source down here, for example, a hydrogen car that is next to a hydrogen filling station, right, and they are filling the hydrogen into the car now, the filling station should not have a structure that is capable of collecting maybe hydrogen that is coming out. So of course you have to make sure that all of this is gas tight and that no hydrogen is being released. But maybe 1 or 2 molecules get out and are released, and they will go up very quickly. We just showed with the foam it's lighter than air. So if you have up here a roof structure that is like that, hydrogen can accumulate, and you could get an explosive mixture by accumulating the hydrogen under a roof. You don't want that. Okay, so what you do is you just construct your roof differently, and you have your hydrogen filling station like that, that the roof looks like that. Okay, and then you have here the other roof, you have here the other filling station, and then the hydrogen will just go up and be released into the atmosphere. You lose some of your energy, you lose some of the hydrogen, of course, but you never get an explosive mixture. You should still put here probably hydrogen sensors that connect to the valves, that connect to the electrical circuits, and so on. I said the lower explosion value is around 4%. So I just released some hydrogen here into the room, and that is no problem, because you can actually calculate the volume of this room, and you take 4% of that, and then you know how much hydrogen you would have to put in here. Of course, hydrogen goes up, so it collects at the top, and there you will reach a higher percentage earlier. And then the next trick is not to ignite it. You saw my foam, it was all inert and it was all happy and nothing happened until I actually ignited it. And if you have some time, I can show you that this even works with Brownian gas, with H2O, H2 and oxygen directly. They also do not ignite, even though it's one of the most explosive mixtures that we know. So yes, hydrogen is dangerous. Always keep that in mind, okay? If you experiment at home with hydrogen, be careful. But it can be solved by technology. So having the correct connection, make sure that everything is connected correctly, have the right valves, have the right connections, have the right sensors, it can be coped with. Batteries are also dangerous. And I mean, diesel and gasoline are ridiculously dangerous. They are poisonous to the humans, they're poisonous to the ground. You do not spill gasoline or anything like that. But we're using it on a daily basis. No one's smoking at gas stations, right? I mean, at least no one's supposed to smoke at gas stations. And you're not taking the gas filling apart and just spill the gasoline all over your car. You know how to handle these dangerous substances on a daily basis. And that is what we need to learn with hydrogen as well. And we can learn that. And then I think it's not a problem. Then we can really deal with that, because hydrogen is something that can be worked with. The role of hydrogen, I need to go just slightly bigger, in the in aviation industry. Yes, so hydrogen in the aviation industry is a good question, because if we want to have a sustainable way to travel long distances, we need a lot of energy. I mean, to get a car moving, we need energy a lot, but to get an entire plane to lift off, that takes huge amounts of energy, and then want to fly across oceans. This does not work with batteries, that's for sure. This works with hydrogen, but if we are going to use ammonia as one hydrogen storage, if we are going to use methanol as hydrogen storage, or if we are going to use the LOHC or the hydrogen directly in a highly compressed 700 bar, we need to see. So for sure, hydrogen is capable of producing something like e-kerosene. So you could fly your planes with the same technology as you're doing it now, even with a CO2 neutral way, by doing, oh, the reaction got lost here, but doing the reaction backwards. CO2 and hydrogen enable us to do the entire carbon-hydrate chains again. But for each carbon we put in, we produce oxygen, we produce water. For each carbon that we put into the chain, we produce water, and we started with water, so it's not a good idea. Slightly more complicated, and if we have a lot of time, we can talk about that in more detail, but complicated story, very simple and short message. Keep your carbon-hydrate chains as short as possible. That's why we want to stay at methanol or at methane. So if you have a plane that's running on methane, that's a good idea, because you can combine one carbon with a lot of hydrogen and you have methane again, you fly your plane on that. Or take methanol, then you have a liquid again at least. So hydrogen is always the first step. Produce hydrogen from renewable sources, use this hydrogen for all kinds of applications. And in the aviation industry, we need higher energy density. So compressed hydrogen is not enough. We need either liquid hydrogen, or we need liquid methanol, liquid ammonia, these kind of solutions, but they are all based on the hydrogen in here. And there is a lot of development going on in these directions. We just have to keep in mind, this is going to be expensive. So we cannot fly for the price that we fly right now across the oceans. We probably will have to pay a higher price, which is more realistic, because right now we only pay for like the oil that the amount of work it takes to get the oil out of the earth. We do not pay for the long-term emissions. We do not pay for the carbon dioxide emissions that we have. The carbon dioxide tax is way too little, so we need to raise that, we need to increase that, we need to have realistic prices for all the fossil energy carriers. And that's all part of this renewable energy system. We have here in our lab the wind turbine that I showed you on a photograph yesterday. We have a big electrolyzer that I also showed you on a photograph yesterday. And we have all the infrastructure in here. That is, if we just take one short look around, Romy, maybe you can take one slow 360-degree turn, so you get an impression on what we see. So there on the right, yeah, slower, then I can maybe walk around and look at things. So over here, this is our smart grid lab. We have the option to simulate the entire electrical grid here with the different players in the grid, and make sure that the wind power plant works together with the CHP, works together with other electrical consumers. Then we have the electrolyzer. We have the battery behind this here, a big one, so we can have this interaction of the different electrical components. And then we can do over here the same thing with all the heat sources and the heat sinks. Yes, because the renewable energy system does not only contain the electrical part, but it also contains a lot of the, and now the quality is really going down, but okay, let's see if that comes back up or not. But the heat part is also quite important, right? You need to have different heat sources. So in our lab here, we have a big solar thermal installation. We have the heat from the CHP. We have the heat from a Stirling engine over there. We have a heat from a normal biomass boiler. We can have electrical heat generation, like power to heat. And we can test all of these things in a scale that is not only lab scale. So you see, right, this guy is bigger than me. This is a 1,000-liter warm water storage. So we do experiments here not only on the small scale, we also do them on the small scale because there it's easier to explain. There it's easier to show and to understand. But in the laboratory scale, it's really nice also for industrial applications to show it does not only work in a small scale, but it also works in a bigger scale. Of course, we're not doing it in a really big scale like the industry is doing, but at least in a certain range. So let me check if there is things in chat or so that we have missed. That is not the case. You got private messages, that's why I can check over here. So this is where all the technology is happening here. Yeah, the quality is not the best. We are kind of aware of that. We have to see how that works or doesn't work. I hope at least you can hear me well. We have to cope with these technical difficulties, and so that was mainly the part that we wanted to show here in our lab. There was a quick tour through some of the installations that we have. There's many more things to see, but then we need to go around, and then the connection to the camera is even worse. So I hope you got an impression on what we are doing here, on some of the installations that we have. And yes, I can see on the screen now that we really are only transmitting at a very low level. I don't know why that is the case, if I would rejoin maybe or not. But I think we don't need to spend much time fiddling with the technology here. Let's rather show some more experiments with the hydrogen. Let's show over here. Yes, just moving a bit more quickly. You have to see if that works. There we go. A little fun experiment for the end, and it doesn't have to be the end. Please feel free always to ask further questions. We have here another electrolyzer. I mean, as you probably have learned now, we have many different electrolyzers and all kinds of technology, but this one does not separate the gases. So this one has, through this nozzle here, directly the emission of hydrogen and oxygen comes directly out here. And you see, it does not ignite. So let's see what happens if we take a catalyst close to it. And maybe we have to do it a few times so the camera picks it up. So if we take a catalyst close to it, we can see it does ignite. The flame is difficult to see. The hydrogen flame itself is not such a nice flame, but it is really, really hot. So you can see that this piece of metal I can easily melt, and I can, this spoke from a wheel, I can really get to these high temperatures. So this is, if you burn hydrogen and oxygen together, this really hot flame. But if I turn it off and on again, it does not ignite by itself. You need some energy. You would need like a flame. If I would have a match or lighter here, I could ignite it, of course. But what you can do with a catalyst is you take the energy that's in the room already, and you have here a piece of a membrane from an electrolyzer. It has platinum on it, and this platinum works as a catalyst to reduce the ignition temperature down to a level where the room temperature is enough to ignite this gas. So with this, we can show that also even that part is safe also. Then we have another mobility application here in this little golf cart that also drives around based on a fuel cell and on hydrogen. This is really nice because you can take 3 people with you, and we use this one to drive politicians around over the campus, and it's a very nice showcase to show everyone hydrogen works as a mobility solution. Hydrogen works as an energy storage solution, and not only on a small scale as we did it here in this little experiment, where you can see now we really have collected a lot of hydrogen. So now we could really switch off the lamp here. Let's switch that on off, and there you go. Now we have a lot of hydrogen collected up here, and we could run our motor for a long time using the fuel cells. And with that, there seems to be no further questions, and the quality has not improved. I see it's still kind of bad from my side. I want to thank you for your attention, for taking part in this. I hope I could also ignite in you a little spark towards the hydrogen technology, towards the renewable energies, which are a very important part of our sustainable future, of living on this planet for many more generations and not using up all the resources and leaving a wasteland for the coming generations. This must not be our task. We should really take care of this planet. And of course, if we want to keep our development going on, if we want to be an industry nation as well in the upcoming years, we need the energy. But this energy needs to come from renewable sources, and hydrogen will play a crucial role in that, because the hydrogen gives us the option to connect the electrical sector with the mobility sector, together with the industry and the heat sector. This is what's called sector coupling. All of that together is happening in the renewable energy system. And I want to thank you for your attention. I want to thank you for your interest. And I hope to give some of you at some stage an in presence show of our laboratory. Feel free to come to us. You know how to contact us. Come to us, look at the lab, take part in our experiments at some stage, maybe together. We have our own spring school that is starting now in September, so that is right around the corner. That is probably not good for you anymore, but we will have that spring school again next year in spring, where it actually belongs. And if the pandemic situation allows, we will have 2 weeks of very compressed information towards the renewable energies. We will have international lecturers. We will have the option to work here with all of our lab equipment, and you can get some credits for that. It's 2 weeks in April, so look at the informations soon on our website to get more information on that. That's our spring school here at the university. You can also join us for 1 semester. You can also study your master's degree here. I already mentioned yesterday our master's course, Renewable Energies and Electromobility. Feel free to join us here in Stralsund for your final semesters. Or if you're interested in a research project and you have just a good idea and you say, look, I want to do my PhD, I have a university that gives out the degree, and I want to do my research with you because there's all of that interesting stuff going on here, feel free to come to us and join us here. Now the chat has been active, but that is a lot of thank you. That is good. Okay. Yes, you're welcome. And I'm hoping to see a lot of you here at some stage in presence. Thanks and bye from my side.